Next, divergence. We have seen yesterday the divergence. Okay, so that is nothing but the gradient of d vector is equal to, okay, uh, that is nothing but d vector ds vector closed loop integral and change in the volume and the volume tending to infinity. So that's volume tending to zero. So this is what we have discussed, and this is divergence. Okay, and we also seen the gradient of the flux density, that is divergence, is equal to what, the rho b, that is volume charge density. So this is nothing but what? What is this?
Maxwell's first equation.
Yes, it is Maxwell's first equation. Okay, and lastly, we have derived the divergence theorem. So that is a closed integral. So ds vector is equal to, and that surface integral comes your volume integral like this. Okay, this is a divergence theorem. Okay, Gauss divergence theorem. Okay, so this is what we have discussed so far, and we have solved the few problems on Cartesian coordinates. So this is your left part of the divergence theorem, and this is the right part of the divergence theorem. Okay, so Gauss divergence theorem. So we have discussed. Okay, yes. Also, we should recall what is that divergence. What is the divergence? So divergence of a vector, that is equal to, so d dou by dou x of x component, and dou by dou y of ay component, y component, and dou by dou z of az components. So there is nothing but, if you know the a vector, you can find the divergence of that vector using this relationship. Okay, you have to know that the components of A in x, y, and z direction. That is your generally any vector will be having the components of x, y, and z. So you can find divergence of any vector. Okay. Yes, this is what we have discussed so far. Okay. Next, also we have seen the divergence in different coordinate systems. Divergence in different coordinate systems. So this is in Cartesian coordinates, and if you want to have the divergence in cylindrical coordinate systems, it will be given like this. So it is nothing but 1 by r into dou by dr, okay, r into ar, plus 1 by r into dou into a phi by d phi, plus dou by dou z of az. Okay, this is in cylindrical coordinate system. Cylindrical coordinate system. So if I want in spherical coordinate systems, so it is the same thing. So it is 1 by r square dou by dou r square into ar, plus 1 by r sine theta, sine theta into, that is component of A in theta direction plus 1 by r sine theta rho by rho phi of a phi. Okay, this is in spherical coordinates. Just copy down. This is very important. We have to solve this one using these equations. So just copy down this one. Okay. So if you have copied, please type 0 on the chat box quickly. Yes. So we should solve some problems here. Yes. So let us solve one problem here. So given d vector is equal to 5r square into ar cap millicoulomb per meter square, okay, for r less than 0.08 meters. So there is a flux density, okay, in r direction of 5r square millicoulomb per meter square for r less than 0.08 meters. Okay. So one more flux density is given. Given d vector is equal to 0.1 divided by r square uh, along the r direction, that is ar cap, millicoulomb per meter square for r greater than 0.08 meters. Okay. So you are supposed to find the charge density rho v when r is equal to 0.06 meters. That is, you are supposed to find rho v at r is equal to 0.06 meters. And again, you are supposed to find charge density rho v when r is equal to zero point 0.1 meters. This is the first question, then this is the second question. Okay. So what is this you have been given? So you are given the d vector you're supposed to find the charge density at two different points, that is r is equal to 0.06 meters and r is equal to zero point 0.1 meters. So the coordinates are assumed to be in spherical coordinates. That is why r is given. So ar is also given. So what is that we are doing? We are assuming that it is in spherical coordinates. You can also assume that in cylindrical coordinates also. We are assuming in symmetrical coordinate system, and we are supposed to find that rho v. Okay, so rho v at two different radii. One radius at r is equal to 0.06 meter, and again radius at 0.1 meter. What is the charge density using the flux density? Okay, so you are given the flux density, you can find the divergence of the flux density. Why? Because the divergence of the flux density is related to the charge density. Okay, because from Maxwell's first equation, so the divergence of the flux density is related to the volume charge density. So you can make use of the Maxwell's first equation, that is um, gradient of d vector is equal to rho v. So this is the Maxwell's first equation, or it is nothing but the Gauss law in point form. Gauss law in point form. So using this, you can find rho v. Okay. Yes, sir. This is how you can make use of the Maxwell's first equation. So now let us find the gradient of d vector for the first case. Okay, gradient of d vector. So for r is equal to 0.06, you are supposed to find r is equal to 0.06. For r is equal to 0.06, you have to find uh, rho v. So you have to find, that means the flux density you have to use. That is the first equation. That is here the flux density is given by 5r square in the direction of r millicoulomb per meter square. Okay, so the gradient of this one. So we have got the standard expression. The standard expression is this one. So cylindrical, so spherical coordinates. So you have to make use of this expression, 1 by r square into dou by dou r of r square into ar. That is nothing but a is nothing but d here. Okay, the component along the theta and the component along the phi is absent. Okay, so what is that we have now? The gradient of d vector is along only the radius part. So obviously we have to use that one, 1 by r square into dou by dou r of the component of dr only. And the component of d along theta and phi is 0. So 1 by r square dou by dou r into dr we know for the region. This is r is equal to 0.06, and the flux density is given whenever this r is less than 0.08. This is what phi r square into ar cap. So phi r square, so it is nothing but uh, r square into dr. Sorry, it is r square into dr. So r square into 5r square into AR cap. Okay, so this is what we have got. So AR cap into AR cap is 1. Okay, so 1 by R square into dou by dou R into 5 r to the power of 4. So it is nothing but 20 r cube by r square. It is nothing but 20 r. Okay, so I repeat here, I am making use of Maxwell's first equation to find rho v. On that, I need to find the gradient of d vector. Okay, so this is the expression for gradient of d vector uh, using spherical coordinates. I got this one. So this is what 20 r. Okay, so this is my expression for rho v. So gradient of d vector is equal to rho v, that is equal to 20 r. So now r is here 0.06. So 0.06. So that is nothing but 1.2 millicoulomb per meter cube. 1.2 millicoulomb per meter cube. So this is the first part of the problem. Okay, when r is equal to 0.06. So when you are to find rho v at r is equal to zero point 0.1 in this region that is here, d vector is equal to zero point 0.1 by r square into ar cap. Use the same expression, that is gradient of d vector is equal to 1 by r square dou by dou r square into dr. Substitute dr and partially differentiate, you will get as 0. Okay, so the it gets cancelled out, so you'll be getting constant. So obviously differentiation of the constant is 0. Therefore, the charge density is 0 for r is equal to 0.1 meter. Okay, this is how we have solved here. Okay, for the charge density for radius greater than or radius point at 0.1 meters, the charge density is 0. Here, yes, I'll just leave at this slide, the previous slide. If you have got any doubts, you can ask me. Is this clear? If it is clear, please type 0 on the chat box. We'll move further. Yes.
Sir, I don't know how to write why the dr is.
What is that?
Sir, according to equation, what about the sine theta and phi angle? Theta and phi angle.
This one.
Yes, sir.
Last one.
Yes, sir. Yes, sir.
The spherical coordinates.
So, but in equation we have replaced by dr. I don't know how, why.
According to
Sir,
ಸಂತೋಷ್
but in
ಕೇಳಿಸಲ್ಲ ಕರೆಕ್ಟ್.
hello, sir. Please, sir.
ಸ್ವಲ್ಪ ಜೋರ ಮಾತಾಡಿ.
Hello.
ಹೇಳಿ.
ಸರ್ ಅದು ಇಲ್ಲಿ ಸೈನ್ ಎ ಥೀಟಾ ಮತ್ತು ಸೈನ್ ಇಲ್ಲಿ ಫೈ ಆಂಗಲ್ ಇದೆ ಸರ್ ಅದೆಲ್ಲ
ಹಾ,
ಕ್ಯಾನ್ಸಲ್ ಆಗಿ ಬರೀ ಈಕ್ವೇಶನ್ ಅಲ್ಲಿ ಆರ್ ಸ್ಕ್ವೇರ್ ಇಂಟು ಡಿ ಆರ್ ಬರ್ತಿದೆ ಅದು ಗೊತ್ತಾಗ್ಲಿಲ್ಲ ಸರ್.
ಅದು ಏನಕ್ಕೆ ಅಂದ್ರೆ ನಿಮ್ಗೆ ನೋಡಿ ಅದು ಫ್ಲಕ್ಸ್ ಡೆನ್ಸಿಟಿ ಕೊಟ್ಟಿರಲ್ಲ.
ಎಸ್ ಸರ್.
ಆ ಫ್ಲಕ್ಸ್ ಡೆನ್ಸಿಟಿ ಕಾಂಪೊನೆಂಟ್ ಫ್ಲಕ್ಸ್ ಡೆನ್ಸಿಟಿಲಿ ನಿಮ್ಗೆ ಸ್ಪೆರಿಕಲ್ ಕೋಆರ್ಡಿನೇಟ್ಸ್ ಆದ್ರೆ 6 ಥೀಟಾ ಮತ್ತೆ 5 ಬರಬೇಕು.
ಎಸ್ ಸರ್.
ಕರೆಕ್ಟಾ?
ಎಸ್
ಬಟ್ ಫ್ಲಕ್ಸ್ ಡೆನ್ಸಿಟಿ ಕೊಟ್ಟಿರೋ ವ್ಯಾಲ್ಯೂಸ್ ಅಲ್ಲಿ 5r² ಇಂಟು AR ಕ್ಯಾಪ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. ಅಂದ್ರೆ ನಿಮ್ಗೆ ಆರ್ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಮಾತ್ರ ನಿಮ್ಗೆ ಒಂದು ಫ್ಲಕ್ಸ್ ಡೆನ್ಸಿಟಿ ಇದೆ ಅಂತ.
ಓಕೆ ಸರ್.
ಥೀಟಾ ಮತ್ತೆ 5 ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಫ್ಲಕ್ಸ್ ಡೆನ್ಸಿಟಿ ಇಲ್ಲ ಅಂತ ಅರ್ಥ.
ಓಕೆ ಸರ್.
ಸೊ ಹಾಗಾಗಿ ನಿಮ್ಗೆ ಆ ಗ್ರೇಡಿಯಂಟ್ ಇದ್ರಲ್ಲಿ you just have to eliminate the component of D along theta and along phi. It is absent anta.
ಓಕೆ ಓಕೆ ಸರ್.
Okay, therefore D theta is equal to 0 and D phi is equal to 0. So we're
ಓಕೆ
getting only dr. Dr is equal to pi r square.
ಓಕೆ ಸರ್.
The first case. In the
ಓಕೆ ಸರ್.
second case, dr is equal to 0.1 into r square.
ಓಕೆ ಸರ್.
Okay.
ಓಕೆ ಸರ್.
Yes. So let us solve one more problem on Gauss divergence theorem. On Gauss divergence theorem. Okay, take down the problem. Given A vector is equal to 30 into e power minus r into AR cap minus 2 into z into AZ cap. Okay. Evaluate both sides of divergence theorem. Both sides of divergence theorem. Okay. For the volume enclosed by r is equal to 2, z is equal to 0, z is equal to 5. Okay. So this is given. This is the question is given. So you have been given this A vector and it is in cylindrical coordinates. It is in cylindrical coordinates. Why? Because your A vector has R component and your A vector has Z component. So there is no theta component. So you can assume that A theta is equal to 0 here. Okay. And what is being asked here? You are asked to solve for divergence. You have to verify divergence theorem on both the sides. So we have written the divergence theorem like this, the last one. This is the divergence theorem. So I'll write it again. So I will write it again. So Here, the divergence theorem is like this. So closed loop surface integral of d vector and ds vector that can be reduced to volume integral when you take gradient of d vector along the entire volume dv. So you have to verify, or you have to evaluate this part as well as this part, that will be equal at the end. So first you have to verify this part and or find out this part, and secondly you have to find this part, so that you can evaluate the left side and the right side of the divergence theorem for the volume enclosed by r is equal to 2, z is equal to 0, and z is equal to 5. So that is a cylinder of radius 2 meters or 2 units, and the base of the cylinder is on z is equal to 0 plane, and the top of the cylinder is on z is equal to 5 plane. Okay, so let me write the cylinder like this. So what is that I am having? So this is x, y and z. So I am having a cylinder, okay, so which is sitting on the xy plane, that is at z is equal to 0. So this is nothing but what? Z is equal to 0 plane. So I assume that the base of the cylinder is sitting on the xy plane or z is equal to 0 plane. Okay. Now the top of the cylinder is at one more plane. That plane is at z is equal to 5. So you are having one more top surface of the cylinder that is lying on xy plane situated at z is equal to 5. This is z is equal to 0 plane. Okay, so this is one plane which is at z is equal to 5, and this is another plane which is at z is equal to 0, and this is obviously a cylinder. Okay, yes, so this is a cylinder, and whose radius is given, that is r is equal to 2 units. Okay, yes. Now you are supposed to evaluate you're supposed to evaluate the left side of divergence theorem separately and right side of the divergence theorem separately. Okay, yes, let us evaluate the left side first, and then we can come back to the right side. Okay, yes, instead of d here, it is given as a. That's all. Don't get confused with the denotation. Instead of d, it is given as a. Okay, so let us evaluate the first part. So are you able to visualize this sphere whose bottom is on z is equal to 0 plane and whose top surface is on z is equal to 5 plane, and the radius is supposed to be 2 units. Okay, yes. So if it is clear for you, this assumption or imagination, you can type 0 on the chat box quickly. Yes. Now let us move forward to evaluate the closed loop surface integral A vector into ds vector, A vector into ds vector. So how many surfaces you find in this cylinder? This is surface integral. How many surfaces you find in the cylinder?
3, sir.
3.
Yes. One is the top surface, one is the bottom surface, and other one is the side surface. Okay. So that is what we have got. So obviously you'll get three integrals, one for the side surface, one for the bottom surface, and one for the top surface. So that has to be evaluated for the whole surface area, that is A vector into ds vector. Okay. Yes. So let us evaluate first the side surface. So side surface is A vector into ds vector. Okay. Yes. So that is equal to. So there are side surface. So which runs here. So for 5 and z, the height is z here, and the azimuthal angle, this is phi here. So you'll be getting two integrals here for the side surface, one varying from 0 to 360 degree. Phi is varying from what 0 to 360 degree, and for the surface, what I'm considering, z is also important. So it is varying from what 0 to 5 here, 0 to 5 here. Okay. So that is what we are interested in now. So it is nothing but A vector into ds vector we have to take. So what is A vector? It is given. It is nothing but 30 into e power minus r into ar cap minus 2z into az cap. So this is A vector is over dot product ds vector. What is that ds vector? That is a surface vector normal. Okay, surface vector normal to the AR direction. So that means, for example, here in this case, this is a surface. This is curved surface. So the curved surface will have the normal like this. It is along the AR cap. Okay, the normal to the surface, side surface, will be along the R direction. Therefore, your ds vector will be equal to R into d phi into dz into AR cap. I repeat here, the surface area of the side, what we are considering is R into d phi into dz into AR cap. Why this AR cap? Because the normal to the surface will be aligned to the direction of your radial vector. Okay. Yes, this is what the ds vector. Okay. So now you have to integrate this one along two limits. One limit is for the azimuthal angle, phi is equal to 0 to 2 pi, and another is for z is equal to 0 to find. Okay. First, take the dot product of this vector and this vector, and you can simplify and apply the limits. You will get the answer. Okay. Yes. So what is that you are going to get here? Pi is equal to 0 to 2 pi, and z is equal to 0 to 5. You take the dot product of it, you'll be getting 30 times into r into e power minus r into d phi into dz. Okay, so this is what you get, and if you simplify it, okay, you'll and substitute r is equal to 2, you'll be getting as 255.1. 255.1. Okay, it is a scalar. Again, it is a scalar. I just put this slide for a few minutes. Just check out. What is AR cap into AZ cap?
Zeros.
Yes. So you will not be getting that component. So AR into AZ. Okay. Therefore, so you can directly simplify and it will becomes easy for you. So 255.1 is your divergence along the curved surface. Divergence along the curved surface. Okay. Next. Let us find the divergence along the top surface. Divergence along the top surface, it is A vector into ds vector, that is equal to, okay. So take the A vector and take the ds vector. Okay. So what is the top surface here? Just check out here. This is my top surface, and how the normal component to this one will be there. So the normal component will be like this. The normal component will be like this, and it will be as AZ cap. The normal component will be along this Z direction. Okay. So therefore, your ds vector gets changed. Therefore, your ds vector gets changed. That is r into dr into d phi into az cap. Okay, r into dr into d phi into az cap, and a vector will remain as it is, 30 times into e power minus r into ar cap minus 2z into az cap, and it has to be evaluated along two directions. One along the azimuthal angle, that is phi, that is 0 to 2 pi, and another variable quantity is radius, is r is equal to 0 to 2 here. R is equal to 0 to 2 here. So if you simplify phi and r here, you get minus 2 into z into r into dr into d phi. You'll be solving it as minus 40 into pi. Okay, this is the top surface. Okay, so now the bottom surface. So bottom surface, so this is at Z is equal to 5. Bottom surface similar. Yes, can somebody let me know what would be this one? Bottom surface, same thing, but
minus
we will,
AZ.
yes, it is minus AZ. So obviously the equation here gets positive here. So 5 and R, and it is 2 into Z into R into dr into d5, and here Z is equal to 0, and here Z is equal to 0. One second. So here Z is equal to 0. So you'll not be having any component of that is the value of Z. So therefore, the total value would be 0. Okay. Yes. So bottom component, top component, and the curved surface. So if you add it. So yes, total surface ds is equal to top plus bottom plus side, that is equal to 255 minus 1 minus 45 plus 0, that is equal to 129.43 units. Okay, this is nothing but left hand side of the divergence theorem. Left hand side of the divergence theorem. So I'll just hold this slide for a few minutes. You've got any doubts, you can ask me. Okay. If it is clear for you, please type 0 in the chat box quickly.
ಸರ್ ನೀವು ಮ್ಯೂಟ್ ಮಾಡಿದ್ದೀರಾ ಸರ್?
Okay. Yes. So this is to evaluate the right side of the component of the divergence theorem. So it's a volume integral, and you have got a divergence of A separately and along the total volume. So I'm having like this, and this is a standard one I'm using for cylindrical coordinates. So it is R into AR. It is component of A along R. Component of A along R. That is nothing but 30 into e power minus R plus 1 by R dou by dou phi. That is component of A along phi. That is 0 from the given expression, and dou by dou Z, component of A along Z, that is minus 2Z. So if you simplify it after partial differentiation, you will be getting it as that is gradient of A vector minus 30 into e power minus R plus 30 by R into e power minus R minus 2. Okay. So now put this in volume integral. Okay. So volume integral, three integrals are there. One for Z, one for phi, one for R, and you know this value. And the dV, let us know what is that. So one for Z, one for phi, one for R, and this one I will just repeat here, minus 30 e power minus R plus 30 by R e power minus R minus 2. Okay. dV, volume of the cylinder, that is R into dr into d phi into dz. This is volume of the cylinder, R into dr into d phi into dz. So triple integration. So you'll be getting it as um, and substitution z is equal to 0 to 5, phi is equal to 0 to 2 pi, r is equal to 0 to 2. So if you substitute the limits and integrate it by parts, you'll be getting it as 129.437. So this is the right side of the theorem. So both are verified. Both are verified. Okay. So this is on divergence theorem. I just hold it for 2 minutes. Please. Okay, if it is clear for you, please type 0 on the chat box. Yes, last problem on divergence theorem, and we shall stop at this point after this one. If take down if D is equal to D is equal to that is D vector is equal to x into y square into z square ax cap plus x square into y into z square into ay cap plus x square into y square into z az cap coulomb per meter square. Find rho v, find q within the cube, find q within the cube, x limits are given and y limits are given and z limits are also given. Okay, so direct problem. So I shall stop at this point. I think we have solved this one. Apply Maxwell's first equation and you can get the answer. So I'll just stop at this point. This completes the Gauss theorem, that is Gauss divergence theorem, and electric flux density is over. Just verify the syllabus being covered here. Only 12 hours chapter is covered. Now we need to move on to energy and potential and current and conductors, dielectrics and capacitance, Poisson's and Laplace equations, like that. So we have been able to cover only this part. 12 hours of unit is covered. Okay. So from here on, we can go at a different pace because until here, you require a lot of fundamentals, understanding and recalling of the fundamental concepts here. So from here on, it will be easy for you because you have got a good good exposure about the different parameters, different terms and terminologies. So it will be easy for you to grasp the concepts from here on. So we'll move at a different pace. Okay. Yes. So this is energy and potential from next class. Okay. Yes. I'll just let you know the next class details. So tomorrow might be I'll be engaging one more class to make up the last classes. I'll just let you know the details. Okay. So I'll stop at this point. You can exit for the next class. Thank you.